Welcome back to our live broadcast on YouTube. Following on from our insightful Zoom sessions, we now move to on our next invited speech, further enriching our scientific journey. Now, we are delighted to invite Professor Huseyin HIZIROGLU for his speech titled Electrical Properties of Polypropylene Loaded with Nanometric Clay, marking the final invited speech of our ELECO 2023 conference. His presentation promises to bring insightful perspectives to the field of materials science, providing a fitting culmination to our series of expert talks. And it's a great pleasure to invite Associate Professor Hasbi ISMAILOGLU from Yalova University to chair this session. His knowledge and leadership will undoubtedly enrich our discussions.
Hello, everybody. Dear guests, welcome to ELECO 2023 conference. I am pleased to start the last invited presentation of our conference. And the presentation title is Electrical Properties of Polypropylene Loaded with Nanometric Clay. The presentation will be made by Professor Dr. Huseyin HIZIROGLU from Kettering University, Michigan, USA. Before starting the speech, let me give a short bio of Professor HIZIROGLU. Professor Dr. Huseyin HIZIROGLU graduated from Gazi University with a BS, Middle East Technical University with an MS, and Wayne State University with a PhD, all in electrical engineering. He joined Kettering University in 1982. Since then, he has been on faculty of Department of Electrical and Computer Engineering and was promoted to the rank of professor in 1991. He has 4-year industrial experience in transformer manufacturing division of Turkish Electricity Authority. His ongoing experimental and theoretical research is focused on the study of electrical properties of polymeric dielectrics to predict the aging. He was also responsible for modeling and integrating power electronic circuits with fuel cells and solar cells as part of a renewable energy resources program at Kettering University. His solar activities has been funded by such industrial companies as General Motors, 100K ADIs, etc., and such government agencies as the National Science Foundation, etc. Professor HIZIROGLU is a co-author of a book entitled Electric Machinery and Transformers, 3rd edition, 2001, by Oxford University Press, and another book entitled Electromagnetic Field Theory Fundamentals, 2nd edition, 2004, by Cambridge University Press. These two books have been translated into Spanish, Korean, and Chinese by Oxford University Press, as well as by Cambridge University Press. Also, he has over 70 articles published in such reputable journals of IEEE Transactions, Journal of Electrostatics, Journal Physics of Plasmas, Journal Polymers, etc., and international IEEE conference proceedings. He has been an invited speaker at numerous international and national institutions, as well as consultant to the United Nations. He was a member of Executive Committee, General Chairman, and is now a permanent board member of IEEE Conference on Electrical Insulation and Dielectrics Phenomena. He is also the past Publication Committee Chair and a member at large of Administrative Committee of IEEE Dielectric and Electrical Insulation Society. Furthermore, he has been co-author of IEEE Transaction of Dielectrics and Electrical Insulation, responsible for Part A, Dielectric Fundamentals. HIZIROGLU is a life senior member of IEEE. Today, Professor HIZIROGLU will give us an important speech on the breakdown behavior of polypropylene and its composites with natural nanometric clay. Let me start the session. Thank you very much.
Thank you very much, Professor ISMAILOGLU, for this nice introduction. And it's a pleasure to be part of this conference, ELECO 2023. I was here in Bursa in 1999, again as an invited speaker to ELECO. But since then, I didn't have the opportunity to come and give a talk at ELECO. But this year, I was really looking forward to be in Bursa again, but in the last minute, because of the restrictions and other stuff, the conference turned into 100% virtual. But nevertheless, I am joining you virtually from Michigan, United States. So it's really a great pleasure for me. And also, I must thank to the organizers of the conference for inviting me as an invited speaker to the conference, and especially the general chair, the Dr. Kalenderoğlu, and the Chamber of Electrical Engineers in Bursa. And the last few days, we've been doing some rehearsing with Mr. Doğakan Ulupınar. So thank you very much for organizing this conference in that virtual platform. It's not easy. I know it, how difficult it is in the virtual platform. During the pandemic, we had done the conference on electrical insulation and dielectric phenomena in the virtual platform internationally. So it's sometimes difficult to do it, virtually. Okay, so without going any further, I'd like to start talking about my, for talk, the electrical properties of polypropylene loaded with nanometric clay. So this talk is really related to a work that we had started like a hobby about, I think like 12, 13 years ago with a colleague of mine and also a friend, the Professor Yusuf Shkolnik, who is a condensed matter physicist. Unfortunately, he's not with us anymore. He passed away several years ago. So then over the years, the work has evolved, and from this for work, we had published numerous articles, and still this is an ongoing work for its aging of the material. So let's just start talking about a little bit of nano materials. And nowadays, nano is kind of a buzzword. Everybody uses nano for everything. And now nano is also in the dielectrics, dielectric materials for almost now, I would say 25, 30 years or so. So nanoparticles have found a wide variety of applications in order to modify the properties of polymer dielectrics. So that's how it started. By another fellow dielectrician, the Professor T.J. Lewis, who also passed away a few years ago at the age some 90 plus, I think. He was very active until the very last minute of his life. So it's also known that the addition of nanoparticles in polymers seems to enhance the overall properties of the composites. In such a nanocomposite, interfaces between two phases, one being the nanoparticle and the other being the host polymer, play a significant role on its properties. So that is basically the interfaces causing the changes in the properties. So this is primarily due to the fact that the volume of interfaces dominates the whole volume of the composite as the size of the nanoparticle reduces. So as you reduce the size, you can put more nanoparticles in it, and therefore you will have more interfaces, boundaries between the polymeric material and the nanoparticle. So that way, the volume of the interfaces will become pretty large and enhancing the properties of the material. This effect could also substantially modify the overall dielectric characteristics of the composite material. And at present, polymeric materials used in cables in high voltage applications are primarily various versions of polyethylene with cross-linked polyethylene, the so-called XLPE, being one of the most widely used because of its favorable thermal properties as compared to the LDPE, the low density polyethylene, and high density polyethylene. With the present technologies, the most powerful extruded cables with polyethylene as an insulating material used in high voltage direct current systems can handle up to like 640 kilovolts. So HVDC, and it is very important in Europe, in China, also in the US, and generally speaking in North America these days, the HVDC, high voltage DC transmission. In China, they have transmission lines operating at 1 million volt and above with DC, plus and minus DC, over a long distance. And so they have their own difficulties, of course, their challenges operating those type of systems. However, there is very little information on the electrical breakdown and the current density in polypropylene mixtures with nanoparticles, and it needs to be further studied. And the polypropylene has been primarily used in RF capacitors, radio frequency capacitors, as the dielectric medium. However, polypropylene has also found lately in applications like cables, found a place in cables. But again, like I said, we have to do studies in order to improve the properties and better understand what is really happening. So the objectives of the presentation here is to evaluate and compare the breakdown strength, the variation of current density as a function of applied electric field intensity of polypropylene-based nanocomposite films with various contents of nano-sized natural clay in polypropylene. And it's expected that the initial data from this work could be beneficial to better understand polypropylene loaded with 2% by weight and 6% by weight natural clay, so that they can be used with enhanced properties in different applications in electrical industry. So that is our objectives. And now the materials, the experimental setup, and methods. So I'm gonna give you a little bit of explanation of what type of materials we have, what kind of experimental setup we have, and the methods we established in this study. The materials we have, it is basically the polyolefin used in this study is isotactic polypropylene, and the natural nanoclay is montmorillonite, which is presented by this chemical formula for the material. And of course, we did not get this. This is commercially available, so that is what is really happening. So since polypropylene is a hydrophobic material and purified natural clay is hydrophilic, they are immiscible thermodynamically. So in other words, they cannot really get along well because, polypropylene is hydrophobic, meaning that it doesn't really take water and repels the water, whereas purified natural clay is hydrophilic, meaning that it likes water and it absorbs moisture and water and those type of things. And these two don't go along well. So consequently, natural nanoclay needs to be intercalated and later in the process compatibilized. Those are all chemical processes, and usually chemists or chemical engineers provide that service to us. And after the intercalation process of montmorillonite with dimethyl dehydrogenated tallow ammonium chloride, which is commercially known as coleoside 20A, that's its trade name, the natural nanoclay turns into hydrophobic from hydrophilic. So it becomes also hydrophobic, and so it repels water as well. Because in insulating materials, we don't want materials which are hydrophilic, meaning that absorbing water and for house water or harbor water in their content. So after that chemical process, natural nanoclay turns into a hydrophobic material, meaning that it doesn't like water anymore. It repels water, so it does not really absorb and harbor the water in its chemical content. In the next step, compatibilization was done using polyband 3150 material. This is another commercially available element. And also included in the batch was Erganox B225, an antioxidant, in order to avoid the degradation of the nanocomposite due to oxidation, which is very important, especially when used in cable insulation. We don't want to degrade the material due to oxidation. So it is very, very important. In the experimental study, we have 3 sets of samples, and those samples are as follows. Sample 1 was isotactic polypropylene with a trade name of Profax HL451H from Basel as the control sample. Its composition was 87% by weight polypropylene, 0.2% by weight antioxidants, and 12.8% by weight compatibilizer. And sample 2, basically, this is really the sample 1 is the plain polypropylene from our point of view. And sample 2 was a nanocomposite with a composition of 85.3% by weight polypropylene, 0.2% by weight antioxidants, 12% by weight compatibilizers, and 2% by weight nanoclay. So this is a polypropylene as the host material, and polypropylene is doped by 2% by weight of natural nanometric clay. And finally, in sample 3, we have the nanocomposite having 81.8% by weight polypropylene in it, and 0.2% by weight antioxidants, and 12% by weight the compatibilizer, and 6% by weight the nanometric clay. Again, in this case, it's a nanocomposite with the host material being the polypropylene, and we have 6% of nanoclay, included into the polypropylene. And each nanocomposite sample had a thickness of 135 micrometer with a variation of approximately plus or minus 10%. And before situated between 2 stainless steel electrodes, the thickness of each sample was recorded using a precision micrometer. And each electrode had a circular flat surface with a diameter of 33 millimeters and rounded edges in order to minimize the electric field non-uniformity. So in other words, with that 33 millimeter, 2 the plain electrodes with the rounded edges, and the electrode, the nanocomposite material is sandwiched between these 2 electrodes, pretty much guarantees a uniform electric field distribution within the nanocomposite. And the electrode film assembly was immersed into highly refined transformer oil in a stainless steel test cell. And this is the test cell, and you can see here the two electrodes, the stainless steel electrodes, and between the two electrodes we have the whitish looking film, the nanocomposite film, the polypropylene nanocomposite film, and that is the sample. And this is the high voltage terminal, which takes the voltage into the electrode arrangement. And then here we have another port which takes the current from the ground electrode to the instrumentation. And we are using a coaxial cable here through a BNC connector, and all the assembly, electrode and the polypropylene nanocomposite assembly is immersed in oil, and you can see the greenish yellowish color as the highly refined transformer oil. And here we have the experimental setup, the schematic of experimental setup. So this is the principal circuit for the test circuit. And here's the chamber. And we have the electrodes, and that is the test sample. And the top electrode is connected to a metal rod and takes it to the outside world, to the power supply, to get the electric field, to the voltage. Excuse me. Excuse me. Sorry about that. I'm sorry. And the lower electrode is connected to the external world through a coaxial cable and the 1 kilo ohm resistor. And there is an insulator between the lower electrode and the grounded test chamber in order to facilitate the measurement of the current. And we are measuring the current using a shunt resistor, 1 kilo ohm resistor. And here we have a digital precision instrument to measure the voltage across 1 kilo ohm. So whatever the voltage we measured is multiplied by a factor of 10 to the power minus 3, and we get the current in milliamperes, and then we can go to microamperes later on. And here we have a capacitive voltage divider to measure the voltage applied. So here we have another precision instrument to measure the voltage, so that we can accurately measure how much voltage we are applying to the electrode and the specimen arrangement, so that we can predict the electric field in the material. So while increasing the voltage at a rate of rise of 90 volts per second, typically 15 to 20 data points were recorded for the voltage and current from 0 up to the breakdown voltage. And from the experimental results, electric field intensity and the current density were calculated. Because we know the thickness of the test sample, so we can easily predict the electric field there. And we know the surface area of the test sample, and we can easily predict the current density that goes to the test sample. So in order to verify the reproducibility of the experimental results, experiments were performed on 5 different samples with the same amount of nanofiller. Moreover, the breakdown voltages were also recorded with a voltage rate of rise of 1050 volts per second for assessing if there were a significant change on the breakdown voltages. So we did one at 90 volts per second and another one at 1050 volts per second of ramp speed. These breakdown tests were also performed on 5 different samples with the same nanofiller content. And now some of the results and some discussions on that. So since the electric field has almost a uniform distribution in the samples, the breakdown strength can be calculated as V sub B over the D, where E sub B is the breakdown strength or the electric field intensity we have, for in the material if it is not a breakdown voltage. And V sub B is the breakdown voltage or the applied voltage, and D is the thickness of the sample. And here we have 2 breakdown strength results for the different concentrations of nanoclay in the polypropylene. One is at 90 volts per second ramp speed, and the other one is 1050 volts per second ramp speed. And this is 0% nanoclay, which means it is a plain or neat polypropylene. It is just polypropylene. And this data point is taken with 2% by weight nanocomposite. And of course, this is also polypropylene based, 2% nanoclay. And this one is 6% nanoclay in polypropylene. And here we can see that there is a significant increase on the breakdown the strength. Those are breakdown strengths. The plain polypropylene broke down at about 105 kilovolts per millimeter of electric field when we have the ramp speed of 90 volts per second. And when we have a ramp speed of 1050 volts per second, the breakdown strength of the same material went up to about 127 kilovolts per millimeter or so. And a similar trend was observed with the nanocomposite with 2% nanoclay and 6% nanoclay. However, one important thing we observed here is that the increase is quite significant, going from plain polypropylene to 2% nanoclay from both the ramp speeds, but not as much increase on the breakdown strength when we go to 6% nanoclay. So the current leads the applied voltage by 1.5359 radians at 60 hertz. So we also monitor the phase shift between the voltage, applied voltage, and the current we monitored, and we observed that we have about a phase shift of 1.5359 radians at 60 hertz. And of course, the current leads the applied voltage because it's a highly capacitive operation. And because this angle is close to pi over 2 radians, this is very close to pi over 2 radians, which is 90 degrees. And this one is about 88 degrees or so, which is for 90 degrees is for a perfect dielectric where there's no conduction current taking place. But in this case, for current in our case, because this is very close to pi over 2, like a perfect conductor, it is apparent that the conduction current is insignificant as compared to the displacement current, even in our case. And because of that reason, the conduction current at 60 hertz is neglected, and the measured current is considered to be approximately the displacement current alone. And in fact, the amount of error on current introduced with this approximation was calculated to be approximately, again, plus or minus 0.061%, which is negligibly small. So in other words, the approximation we made here at 60 hertz is a fairly good approximation, considering the current that we measure is the displacement current. But in fact, we know there is some conduction current in it as well, but we are neglecting its effect because of that very high, phase angle between the voltage and the current. So once we measure the current I, we can divide that current by the surface area of the test sample, and we can get the current density. And this current density, J, is approximately the displacement current density, which can be given at sinusoidal steady state by this expression, J omega D, where D is the electric flux density. Sometimes people call it as the displacement current density. I'm sorry, displacement vector. J is the displacement current density. But this is, in general term, this is the electric flux density measured in coulombs per square meter. And this electric flux density is also given by the permittivity times the electric field intensity. This is the constitutive property of a dielectric material. And here epsilon is the permittivity of the medium, and E is the applied electric field intensity. And of course, the permittivity can also be expressed as the epsilon zero, the free space permittivity, times 1 plus chi sub E, where chi sub E is the electric susceptibility of the material, which is directly related to the dipole moments, electric dipole moments in the material. And this chi sub E is pretty much like a bulk property of the material. But it is highly associated with the permittivity of the medium. And also here we have the so-called polarization vector, capital P. And that is also epsilon zero times chi sub E, the electric susceptibility, times the electric field intensity. This tells you how polarizable the material is. And this is highly dependent upon the number of dipole moments in the material. In fact, polarization vector is really the volume density of the total dipole moments at a point in a dielectric material. So it is again highly related to the for electric susceptibility of the material. And you can clearly see that depending on the nature of the material, this could be constant, almost constant. This could be an electric field function. So it depends on many factors. And here we have epsilon R, which is really the relative permeability of the material, which is really the permittivity of the material, relative permittivity of the material, which is really the permittivity normalized with respect to the free space permittivity, epsilon zero. So oftentimes people call this loosely as the dielectric constant, but we know it is not a constant in general. But in many cases, people operate the material in an electric field region where this relative permittivity is almost constant. So here we have now some data. So here, this is our plain polypropylene. It is unfilled polypropylene, and the horizontal axis is the electric field intensity, and the vertical axis is the current density. We can also determine the electric flux density in the vertical axis by simply dividing all those current densities by the angular frequency, which is 377 in our case, because here in North America we have 60 hertz. We did the experiments at 60 hertz. At 60 hertz, the angular frequency is 377. So as soon as we divide all the current densities by that, we get the electric flux density, and then we have like D versus E characteristic of the material. But in this slide, I have it in the form of current density, and this current density is essentially the displacement current density because of the reasons I just mentioned, that the conduction current is negligibly small at 60 Hertz, so we took it out. But if we go to high frequency, for example, if you want to do dielectric spectroscopy, we go very high frequencies, kilohertz and even in megahertz, and in those cases we cannot really neglect the conduction current. We have to appropriately take it into consideration. But at 60 hertz, its effect is quite insignificant. So as you can see here, as the electric field is increased, the current density, thereby the dielectric, electric flux density also increases almost linearly up to about 40 kilovolts per millimeter, almost constant increase. But thereafter, it starts bending and it goes into saturation. And here, actually, we ran into a breakdown. The material gave up at this electric field intensity and broke down. And we couldn't really increase the electric field any longer. But if we were to increase, if the material was capable of handling the electric field higher than the breakdown strength, of course, then probably eventually this would saturate and will come to a flat level. So, as you can see, the ratio of the electric flux density D to the electric field intensity is really the permittivity of the material. Up to about this level, it appears to be almost constant, but thereafter, it's no longer constant because of the electric dipoles aligned themselves with the external electric field intensity. And we will have a little bit of a discussion on that. And here we have the relative permittivity of the material as a function of the electric field intensity. And again, you see, the permittivity, the relative permittivity is almost constant here. And as soon as we reach 40 kilovolts per millimeter of electric field intensity, it starts bending, and then the permittivity starts diminishing at a rather fast rate as the field increases. And this is the breakdown, and starting from about 2.25 or so as the relative permittivity, ended up with about 1.4. If we were to go further down, it would be the free space permittivity, because all the electric dipoles would align themselves with the externally applied electric field intensity. So there's no longer any electric dipoles, no electric dipole moments. Therefore, the whatever the electric field you apply would pass through the material and as the electric flux. So electric flux would be saturating. So it is pretty much like the magnetic materials, ferromagnetic materials. Because of that reason, this type of characteristic, often referred to as like ferroelectric characteristic for a dielectric. Do we have any ferrous material and iron material in the material? No, we don't have. But because we have this saturation effect, which is very similar to the magnetization characteristic of a magnetic material, we call this as a ferroelectric behavior for this dielectric material. So it is kind of building an analogy between the two, even though the two phenomena are altogether different. But, different in that sense that here we have the electric dipoles. In ferromagnetic materials, we have the magnetic dipoles leading to this type of characteristic. The physics behind them are different, but the dipole models are similar, but describing altogether different phenomena, physics-wise. So that's why it is really not really a good idea calling epsilon sub r as the dielectric constant if you push the material into this range. But if you are here, it's almost constant, so you can call it as dielectric constant. That's okay. And this is the characteristic for 2% filled material. So again, we have this ferroelectric characteristic, the saturation effect, for going on with the material we have. And again, we have almost a linear region here where the permittivity is almost constant, but thereafter we have a severe nonlinearity, and we see the nonlinear behavior in the permittivity as well. And here you have it. You see, it goes like this. Nevertheless, this type of property oftentimes are required in the material that actually, yes, materials that we call as electrodes, or sometimes they could be a device. Again, it is an established fabricated term through analogy from magnets, and electrodes are great materials in applications like high fidelity speakers and microphones. And it was a breakthrough discovery sometime in 1970s to replace the carbon microphones by electret microphones in various applications to get a better quality of communication. Today, still, there are electret microphones, but there are other technologies established with the digital systems and things like that. So things are changing, and electrets are kind of going away in the audio business, but still we use them. But nevertheless, electrets are now widely used in sensor devices for sensing various different things. And for that, you have to have this type of characteristic. And polypropylene is a very good candidate for an electret, but of course there are other materials, other polymers that can be used as well as electrets. And this is with the 6%, for nanoclay doped polypropylene. We have a similar characteristic here as well. And this is the permittivity, relative permittivity characteristic. And again, it is almost constant in this range. And after like 40, this time it is a little bit higher than 40 kilovolts per millimeter. It starts bending and goes down. And the dielectric breakdown of polypropylene is affected by the polymer morphology when polypropylene is subjected to sinusoidal voltage. And polypropylene usually breaks down electrically in locations where the material is less dense. Okay, and there is another fellow scientist, Andrich, in England, and his team had done similar work in different materials. And also in polypropylene, indicated that the smallest breakdown voltages took place in the interspherulitic zones of polypropylene, whereas the highest breakdown voltages took place in the spherulites regions. So those are the regions where we have more nano particles and creating like spherulites in those areas. Therefore, the improvement observed on the breakdown strength of nanocomposites of polypropylene could be due to the natural nanoclay that fills the regions less dense in polypropylene. So, for example, the polypropylene is really an inhomogeneous material, I would say. And in some places, it is pretty rich. In other places, there are some weak points, and those weak points are filled with nanoclay. And then we can improve the breakdown strength of the material. Otherwise, in the weak points, in those, for interspherulitic regions, we have those breakdowns. And But in the spherulites regions where it is dense, we don't have. We have a higher breakdown voltage, thereby higher breakdown strength of the material. And the dielectric breakdown of polypropylene is affected by the polymer. I think we did this, right? What is happening here? I cannot move it. Okay, now it is moving. Yes, I'm fine. Also, an optimum content of nanoclay is proposed according to the results on the breakdown strengths in this investigation. I'm not sure if we skipped quite a few. No, we are okay. Something happened here, but I'm fine. I'm in the order. That is what I'm supposed to tell you. So optimum content of nanoclay is proposed according to the results on the breakdown strengths in this investigation. It was observed that the breakdown strength did not improve substantially for the nanocomposite filled with 6% by weight nanoclay when compared to 2% by weight nanoclay. And I think you remember that. I can go back quickly and show you that graph here. You can see this is from plain polypropylene. We have a significant increase on the breakdown strength, but from this point, 2% nanoclay to going to 6%, it is not really a significant increase on the breakdown strength. Here also, it's not a significant increase, at least not as much increase as in this range here. So because of that reason, we can claim that 2% in this context of the work appears to be the optimum, for nanocomposite or nanoclay. Therefore, nanocomposite loaded with 2% by weight natural clay was considered to be the optimum amount of natural clay. So we don't really need to load with 6% nanoclay. And when the rate of rise of the applied voltage was increased from 90 volts per second to 1050 volts per second across unfilled polypropylene and its nanocomposite samples, a significant increase was observed on the breakdown strength of the material. The red graph and the dark blue graph, and there was a significant increase going from 105 kilovolts per millimeter approximately for plain polypropylene. It jumped about 127 kilovolts per millimeter in that graph that I just showed you a minute ago. And the increase on breakdown strength is essentially due to the insufficient time to transfer energy to the particles in the unfilled PP as well as its non-natural nanoclay filled samples to initiate the ionization activity when the rate of rise of the applied voltage is higher. Because ramp rate is fast, so there is not enough time to transfer energy to the particles in both the polypropylene and its nanocomposites with natural nanoclay. So the breakdown strength went up because we don't have enough time to cause the ionization. So not enough time to supply the activation energy to the polymeric material to initiate the ionization. So thus higher electric field intensity is required to maintain higher energy for the inception of the ionization activity that might possibly cause a sustained discharge leading to the failure of the material. So that is why we have a higher electric field strength at the higher ramp rate of the applied voltage than the lower rate. And the saturation effect and the current density versus electric field intensity characteristic is in unfilled polypropylene and its nanocomposites loaded with natural nanoclay can be explained based on the net polarization of the materials. As I just mentioned, if we have more electric dipole moments, we will have more polarization. But if the number of electric dipole moments align themselves with the externally applied electric field, then the polarization is really limited to that. And therefore, the saturation effect will start taking place. So it is basically, due to the net polarization of the material. The current density is proportional to the net polarization of the material. Higher the net polarization, higher the current density, the rate of the increase of the current density, and the lower the net polarization, the rate of the increase of the current density becomes smaller and then pushes into the saturation. When the applied electric field is raised starting from 0 up to a certain level, the displacement current density increases linearly since it is directly proportional to the net polarization in the material. We have a constant for rate there. Above a certain electric field intensity, on the other hand, the rate of change of the net polarization with respect to the electric field intensity becomes lower. So the rate of the polarization decreases. Therefore, the rate of the increase of the current density decreases, and then the saturation effect starts occurring in the material. So that's how we can explain it. It is directly related to the rate of the change of the net polarization in the material. And in the linear region of the current density electric field characteristics of the materials, the relative permittivity remains almost constant since the net polarization of the material takes place at a constant rate of change with respect to the electric field. But with respect to a higher electric field, the net enhancement rate of polarization diminishes and leads to a significant reduction in the permittivity of the material. And we observed all those experimentally, as I showed you in the graphs. And some conclusions, and I hope I'm not taking too much time. Some few conclusive remarks, and then we are going to wrap it. So the polypropylene loaded with 2% by weight and 6% by weight natural nanoclay indicated an improved breakdown strength when compared to the unfilled isotactic polypropylene. However, the increase of breakdown strength was more significant as soon as the polypropylene was doped with 2% by weight natural nanoclay, then the increase of nanoclay content to 6% by weight. Also, as the ramp speed of the applied voltage increased, breakdown strength of all the materials under consideration increased because of the reasons I just presented in the previous slides. And the saturation onset in the current density electric field characteristics also seem to be the highest with 2% natural clay in polypropylene. At high electric field intensities, there is a significant drop in the permittivity of polypropylene and its nanocomposites. And I have a few acknowledgements here. And first of all, my late colleague, Professor Yusuf Shikolnik, was one of the contributors to this work. And Dr. Abu Daka, who retired now from Natural Research Council of Canada, is acknowledged due to the supplying the isotactic polypropylene and polypropylene nanocomposite filled with 2% and 6% by weight, the close height. And also the equipment we used in this work was partially funded by National Science Foundation grant from the United States government. So thank you very much for your attention to my talk. If you have any questions, you can bring it to my attention. Thank you very much again for inviting me as an invited speaker to this conference. And also, once again, thank you very much for all the organizers of this conference to make it a successful event. Thank you.
Dear Professor HIZIROGLU, thank you very much for your valuable contribution to our conference. It was nice to see you. I think there are some questions about your presentation. I am not sure if could you see this at the bottom of the. Let me to try to read.
Yes, I read it. I see that.
Okay. Okay.
Yes, I read it. Actually, to tell the truth, we did not really do all this process. The manufacturing of the nanocomposite, as I acknowledge my fellow colleague at the National Research Council of Canada, they had a facility. This requires a facility to make that material. We don't have that facility. And it should be a clean environment. And they manufactured it at the National Research Council, and they supply the material to me. And the proportion of the nanometric particles, as I said, it is 2% by weight in the polymeric material, and 6% in the other nanocomposite. And what's the size of nanometric particles? So there is an average value I can tell you. The average value was somewhere around like 50 to 80 micrometers. I'm sorry, nanometers, not micrometers. Okay. Nanometers, 50 to 80 nanometers of size. That is an average value. It could be, in some cases, lower than that. In other cases, could be higher than that. Typically, if a material is less than like 1 micrometer or 150 nanometer size, considered like a nanoparticle. So that is what the information given to us from National Research Council of Canada.
Thank you very much. Then another question. One more from example, Professor Özcan. What does partial discharge and electrical drying contribute to the characteristics?
Yes. Yeah, we did not look into those aspects. We did not look into the partial discharges. We were just looking into the dielectric behavior, the permittivity, and the breakdown strength of the material. And the main reason of this work, actually, I must tell you, there is one step, for forward of this work, the aging of this material, how it is going to age. And we needed this type of information for our model. In the mathematical model, we needed this type of information to predict the life expectancy of this material. And we are still working on that. And we are still doing some experimental data collection to verify our mathematical model for the aging of it. But we did not look into the partial discharge behavior. We did not look into the electrical treeing. We did not look into any of those.
Thanks a lot. Another question, is there any question? One more from
nanoclay being mixed with other materials. Yes, of course. You can use it with epoxy resins, for example. It is another work people are doing. We are not doing it, but dealing with epoxy resin is easier than polypropylene because it is basically a thermosetting material. You can use nanoclay with epoxy resin as well. At my youth, I did work when I was at the Middle East Technical University doing my master's with epoxy resin. And there we mixed epoxy resin with quartz powder. but the size of the coarse powder was like 1 micrometer at the time. And during those years in the late 1970s, nobody was talking about nanomaterials, nanoparticles, but we had observed some significant changes in the properties of epoxy resin with the addition of coarse powder. And again, there we were not really studying the material. We were using it in casting a potential transformer, a voltage transformer, as a dry type voltage transformer sponsored by Electricity.org at the time. And we did it successfully with mixing epoxy resin with coarse powder. But now you can use nanoparticles, natural clay or synthetic clay. We also have another work with synthetic clay. We published numerous papers in that as well, with synthetic clay in journal Polymers, and some of their similar type of characteristics we presented with synthetic clay. But it is possible to mix, especially epoxy resin. It is fairly straightforward to mix with the nanoparticles, nano clay or nano materials with epoxy resin. So it is possible to do it. It's not just polypropylene. You can do it with anything. Polyethylene, they do it, and so on.
Oh, thank you very much, dear professor.
Yes, there are standards for such materials. And for polyethylene, standards are quite stringent for cable applications. There are IEC standards. There are SIGRE technical group documents. IEEE has some. So there are standards, especially for polyethylene cables. But those are still evolving technologies and evolving standards. They are not really cast and concrete at this time. As things change, as experience matures, then the technical committees, technical standard committees come up with new standards, new additions, and so on. But there are standards even as we speak now on cables, cable applications.
Oh, nice. Thanks a lot.
Thank you very much, the Professor Kalenderli, for your questions. Very, for fruitful questions, very important, and we can discuss in the future if you want as well. We can do Zoom meetings as well as time permits.
It will be nice to see it together. I would like to express our best wishes to Professor HIZIROGLU on the behalf of organizing committee of ELECO. And also I wish like to answer my best wishes to esteemed participants. Thank you very much. Hope to see you
at another
ELECO conference.
Thank you, Dr. ISMAILOGLU, and it was wonderful to see you again after so many years.
Yes, I think about over a quarter of century.
Yes, the first time we met, that was exactly more than a quarter of a century, and Minneapolis at Conference on Electrical Insulation and Dielectric Phenomena. That was the first time we met. I vividly remember that time.
Thank you very much. It was I'm very glad to see you again.
Yes.
And hope to see you face to face soon.
Thank you.
Have a nice time. Bye.
Thank you. Have a good day.
Bye.
And goodbye. Goodbye.
Our deepest appreciation goes to Professor Huseyin HIZIROGLU for his informative speech on polypropylene and its nanometric clay composites. His detailed investigation of their electrical properties has contributed greatly to our understanding of nanocomposite materials. We extend our gratitude to Associate Professor Hasbi ISMAILOGLU for his skillful moderation of the session, enhancing the depth and quality of our dialogue. Ladies and gentlemen, as this conference draws to a close, I'd like to express my deepest gratitude to everyone who has contributed to the success of ELECO 2023. This year, we were privileged to hear from 7 distinguished invited speakers from the scientific community who enriched our understanding and rekindled our passion for science with their invaluable insights. A heartfelt thank you to all our esteemed speakers from around the globe who joined us despite time differences, and to our dedicated session chairs for their invaluable management and contributions. Our thanks also go to participants who presented their groundbreaking studies, and to our attentive audience for their engagement and enthusiasm. Special thanks are due to Mr. Burak Özgen, Chairman of the Chamber of Electrical Engineers Bursa Branch, and the EMOI team for their indispensable contributions to this conference. I would also like to express my sincere gratitude to Professor Özcan Kalenderle, the Chairman of the Organizing Committee, for his exemplary leadership and tireless efforts in making this conference a success. I am also grateful to Emin Sezen and Doğukan Olupınar, the technical team, for their excellent work in facilitating our live broadcast and Zoom sessions. Their contribution have been invaluable. Looking ahead, I eagerly anticipate next year's conference, where we hope to gather again in an environment enriched by the light of science and sharing discoveries. Thank you all for your understanding and passion with any issues we encounter during our live and Zoom sessions. Please remember that our conference will proceed with Zoom sessions, and for more details and the full conference program, do visit www.eleco.org.tr. As we part ways, I wish you all continued inspiration from the world of science. Until we meet again, take care and have a wonderful day.